In this portion of our lecture, we are going to cover the review exercises for Chapter 5, about the normal approximation for data. An explanation of these topics is in practice doing the earlier portion of this lecture or of this chapter can be found in part 1 of the lecture. Jumping right in, I'm looking here at problem number 1. Now we have a list of test scores with an average of 50 and a standard deviation of 10. All right, I can believe that looking at these scores. Let's use the normal approximation to estimate the number of scores within 1.25 standard deviations from average. Well, we don't have to convert any of these scores to z-scores or anything like that. Because we know we can use the normal approximation here, we can use that to help us estimate the number of scores. So let's start out as we do by drawing a normal distribution, or a more or less normal distribution. Then we just want to know the number of scores within 1.25 standard deviations of average. Okay, well, it doesn't really matter what the raw scores are for the average and the standard deviation. We just need to know the z-score, and we do because the z-scores are in standard deviation units or standard units. So here's our mean and our z-score of 1.25 and negative 1.25. And we can find this area by using our z-table. So we're going to find first the z-scores, or first we're going to look up our z-score, 1.25. And then we can either get the mean to z area and double it, or get the outside area and double that and then subtract. I'm going to get the mean to z proportion and use that in our calculations. So I'm here in the z-table. And I found a z-score of 1.25, and the mean to z for a z-score of 1.25 is 39.44%. So if this area is 39.44 and this area here, that means this area over here is also 39.44%. And so together, these two areas are equal to 39.44% times 2. And that's going to be 78.88%. And so that's our estimate of the number of scores within 1.25 standard deviations of average. Now, they want to know how many scores were really within 1.25 standard deviations of the average. Well, to find this one, what we need to do is know what are the raw scores that represent these z-scores. So here we have z. We need to know the raw. So let's remember our formula for finding raw scores is x equals z times the standard deviation plus the mean. So we can find this for each of our z-scores. We have first a z-score of negative 1.25 times our standard deviation of 10 plus 50. So negative 1.25. And when you're converting scores, this is an example of when the negative sign really matters and why we don't want to get in a habit of, just dropping negatives or anything like that. It really matters. You'll come out with a really different answer. As you'll see, we'll come up with different scores for these. So this first one, if we calculate this out, our first z-score, or our first raw score is 37.5. And then for the next part, we'll use our upper limit z-score, 1.25, again times 10, plus 50, our mean. And we get an upper limit raw score of 62.5. Looking good, Candace. You're going to have a whole litter of kittens pretty soon. Really adorable kittens. I'll put some pictures in the next lecture. They're itty bitty babies right now. They still have their little eyes closed. So how many scores were really within 1 1/4 standard deviations of average? Well, we know these raw scores now are 37.5 and 62.5. And we can just look up here. Let's see, what were the scores that fell between these 2 points? Uh, 39. You see, I'm just gonna, well, I'll just underline them. That's 39, 41. So lots of these scores fall within our realm. 37 is below, so we'll leave that out. Nope. 64 is not in between 37 and 62.5 or 37.5. So these are all the scores that fall within our interval. And why do it like this instead of just looking at them and counting? Because you could count these wrong. Remember, this is statistics. We're precise about the data. So let's go ahead and just visually verify, okay, all the scores that are not circled, they are in fact below 37.5 or above 62.5. And I'm going to quickly verify that all the scores in my interval are correct and then count them. 18. 18. So how many scores were really within 1 1/4 standard deviations? 18. And as I'm reading this, because so they asked us here for the number of scores really within that. And in our first interval, our first problem, we stopped a little bit short of the final answer because it does actually say, use the normal approximation to estimate the number of scores. Boy, that's tricky, isn't it? The number of scores within 1 1/4 standard deviations of average. How on earth would we find that? Well, we have the information we need, but we need to do one more step here. And that is to first know how many scores are there total. $25. And so we want to know how many scores fall within our 78% of 25 scores. So to estimate the number of scores within this interval, we know that our total number of scores is 25. I just counted them. And if we want to know how many are within this proportion, we take 25 times the proportion, not the percentage. And then we will have the number that the proportion that falls within any part of the distribution, really, that is equivalent to 78% approximately. For a final answer here of 19.72 scores. And another issue is that to estimate the number of scores, well, obviously we don't have a part of a score within this deviation. We have whole number, they're either 19 scores or 20 scores, so we'll say there's about 20. And when we do the math, we find 18. Does that make sense? Hopefully, yes. Next up, we have review exercise 2. You're looking at, this is why I need to read the problems out loud before I do them. You're looking at a computer printout of 100 test scores, which have been converted to standard units. The first 10 entries are listed below here. We're not going to read those. Does the printout look reasonable, or is something wrong with the computer? Okay, well, how would we know if this looks reasonable or not? The first thing to think about is, let's think about what do we know about the range of standard units? Well, as discussed previously, standard units range from, well, they could range from, they technically could have an infinite range, but standard deviation units, let's say it like this, 6 standard deviation units typically encompasses a whole distribution. So that's equivalent to plus or minus 3 standard deviations. So if we have scores in here that are beyond, that are above 3 or -3, or above 3 or below -3, then they're probably unreasonable scores. Because if we look at, just to help illustrate this point, if we go ahead and look, let's look up a z-score of 3, and let's see what is the proportion of the distribution there. Well, my goodness, if we look up a z-score of 3, then the area beyond Z is 0.13. So that would look like, so here we have our Z-score of 3. I mean, it's even further out here. Let's say this is 3. And it's this teeny proportion here. And at the percentage, actually, which is in our table, it's even a smaller proportion than this. The percentage is 0.13. So if the percentage is, then the proportion would be 0.0013. So a very small bit. This is less than 1% here and less than 1% down here at -3. So as you might imagine, if we got all up to a z-score of -11, or down to a z-score rather of -11, boy, the probability of that score is infinitesimally small. So there's something wrong with the computer. Right, the z-scores are unreasonable. Remember to stop me if you have any questions. But we'll move on to number 3. From the mid-1960s to the early 1990s, there was a slow but steady decline in SAT scores. For example, take the verbal SAT. The average in 1967 was about 543. By 1994, the average was down to about 499. However, the standard deviation stayed close to 110. The drop in averages has a large effect on the tails of the distribution. Okay, let's estimate the percentage of students scoring over 700 in 1967. Okay, well, to do this, we're going to have to convert these to z-scores, and I'm going to have a bit of math here, so I'll make us some extra space. First step here is to take note of our pertinent data. So the average in 1964, and I'm going to label, or 1967, I'm going to label this so I can remember what each one is. So this is 1967, and the mean is 543. The standard deviation was still 110. And we're looking for the z. And our next, we're going to need the z for a score of 700. And so if we work this out, we've got 700 minus 543 over 110. And we end up with a z-score of 1.43. And I'm going to do a quick logic check on this. Does that make sense? Well, 700 is above the mean, so the z-score should be positive. So this does make sense. Now to find the percentage of students scoring over 700, we can just find our z-score. We can look up our z-score and get the area beyond z. Oops. So here we have our z-score 1.43. We want to know the students over 700. Back to our z table. .43, and then our area beyond z is 7.64. Okay. What do you mean, Joe? You were on 3A? We're on 3A right now. Oh, so you were there. That's good. I figured you were hiding in the background. I was just teasing you lightly, hoping to get you to come out of the woodwork. That's all. I knew you were there. Next up, we can estimate our percentage of students over 700 in 1994, and we'll follow the same process, except using our 1994 data. Now we have in 1994 a mean of 499. Again, you might be thinking, why is she rewriting those down there? They're in the problem. Well, because again, when we get into more complicated things where you've got to keep looking, you don't want to have to keep referencing back into a word problem to find your numbers, because then it's easy to get them mixed up. So there's always a method to my madness. At least in statistics, let's say. And we can convert our z-score here. Now we've got, oops, again, what's the raw score we're looking at? 700 minus 499 over 110. And now we have a z-score of 1.83. And to get our percentage of students, we'll do the same process. Here's our curve. And look up a z-score of 1.83. Here it is, 3.36%. There you have it, folks. Now we're going to keep talking about the SAT, but while I get this slide ready, I want to make a note that this information they're saying about the math SAT, men have a distinct edge, perhaps, but I'm going to inform you of some other, just for your personal information on this subject. It's a commonly held misconception that men are better in math. This is not true. Even though it may be true that men do better on the math SAT, I don't know if that's still true, but good research has found that girls and boys, males and females, will score equivalently on a math test when the examples, the math problem examples, are gender neutral. So the issue, the hypothesized issue, is that the examples on the SAT and in many math classes, also true in physics, are examples that come from areas that, if we look at gender norms, are generally in the normative male area. You know, there's a lot of sports examples and things like that. And if we have instead examples that are targeted at a more gender neutral ideology, then the difference in math scores dissipates. So just so you ladies out there don't feel like there's some inherent issue here, there's not. And this research is part of why I try to, when we do examples, and when we, especially as we get into the second half of the class, we'll write more and more of our own examples. We'll try to use examples from our own lives. And why I want you to integrate examples from your work, because the more you integrate and frame this material in examples that are familiar to you, the better you will, in contexts, I should say, that are familiar to you, the easier it is to do the material. So we're set here to do our problem, and we can look at this claim, men have a distinct edge on the math SAT. All right, I'll accept it for the terms of this problem. In 2005, for instance, the men averaged 538 and the women averaged 504. Now let's estimate the percentage of men getting over 700 on this test in 2005. Oops, here we go. So let's keep track of our data for men. Their mean was X bar, and I'm going to put an M here. So these are men, and that helps me identify which column we're in. 538, and the standard deviation. The standard deviation is the same for, okay. You may assume the histograms follow a normal curve and both SDs were about 120. Okay, that's essential. Right? And so we need to find first this Z-score that represents 700. We know Z equals X minus X bar, or the raw score minus the mean over the standard deviation. And when this is calculated out, we have a Z of 1.35. So we can put that on our histogram. It's 1.35 here. And we need the percentage of men getting over that score. And it's 8.85%. And then to get our percentage of women, we can follow the same process. The mean for women, was 504. And just work through this quickly. Same process, but new values for our population. We end up with a Z of 1.63. So again, here's 1.63, and we need the proportion over here. And the proportion to the right there is 5.16%. There we go. Just as a preview of where are we going with this, so right now this is still descriptive, estimating these percentages, but when we move into inferential statistics later in the course, we'll be able to test these proportions to see if there's a statistically significant difference between these proportions. Because just because two numbers are different doesn't mean that their difference is statistically a significant difference based on the various qualities of the data, to be described later in the class. But this is where we're going with these topics to help map this road for you. And now we're back to the Haynes study. Haynes 5, the men aged 18 and over had a height of 69 inches and a standard deviation of 3 inches. Oh, I'm sorry, I forgot to copy the histogram. Or is it here? Yes. So this is the histogram. It didn't fit on the page. Let's copy a miniature version over for us to look at when we're reading it at least. I guess maybe it does fit. It's hard for me to know what's visible on your side, but a larger representation of this is, of course, in your book. In Haynes 5, men aged 18 and over had an average height of 69 inches and a standard deviation of 3 inches. The histogram is shown below. Here's our normal curve. So the histogram is shown below, and just as a point of interest, note that just because you draw a normal curve on top of some data does not make those data normally distributed. You draw the curve on top of the data to help you see if they're normally distributed or not. And this is going to become a crucial distinction in some future labs and later work we'll do. But I like to preview some of these topics so that it's easier when we get to them later. The percentage of men with heights between 66 inches and 72 inches is exactly equal to the area between. Let's see, what scores is that equal to? Well, I'm guessing that 66 and 72 are going to be equal to a standard deviation or so. Here we have it, 66. 66 is -1 standard deviation. 72 is +1 standard deviation. So the area is between -1 and +1. Oh my goodness, I forgot these answers were right here. Remember, the answer options are right here. So easy choice. Area between -1 and +1. Let's draw them over here. Under the C, for C and F, your choices are normal curve or histogram. Ooh, Peanut Gallery, what do you think about C? Are we voting for normal curve or histogram? Just take a guess or make a guess. While you're thinking, I'll provide you with some important information, which is to remember that when we are talking about the normal curve, or when we use z-scores, we are referring to a normal curve, and the theoretical assumptions that it entails. So I'm going with normal curve. Thank you, Candace. Oh, ha ha ha. So, I mean, this is a tricky point. I looked up the answers here. I don't usually look up answers because I figure them out, but this is a little funny. And again, small distinction, but the point they're trying to make here is that we're actually going to, so let's revise a little bit here. So they're saying with a normal curve is exactly equal. If it's exactly equal, then the percentage of men with heights between these two areas is going to be exactly equal to the area between those 2 points, 66 inches and 72 inches under the histogram. This percentage is approximately equal to the normal approximation. That is the area between the z-scores for these problems, so -1 and +1, under the curve. Why this distinction? Well, it has to do with the curve being a theoretical approximation. The histogram is exactly empirically equal. And in terms of troubleshooting, this is an example of how it's easy to get into a pattern of, we've done several problems now where the first step is convert to Z. So, our minds just go straight to, okay, we must be converting to Z again. Not so fast. It's often good after you do a stats problem to just look back and say, okay, does what I did make sense? And just make sure it makes logical sense to you reading through it again. Again, this is a fine point, so. Among applicants to one law school, the average LSAT score was about 169, the standard deviation was about 9, and the highest score was 178. Did the LSAT scores follow the normal curve? Well, how do we approach this one? Well, we need to think about the number of scores that we expect to be in areas of the normal curve, or the proportion of scores. Oops. Thus, here's our essentially normal curve. And we know that how these scores would map out. If this is the mean, 169, one standard deviation is going to be 9 points above that. So it'll be 178. And we would expect 34% of the population, roughly, to fall in between these two scores if this followed a normal curve. However, that's the question. Is this normal? Well, if the highest score was 178, then this probably isn't normal because we would expect we would expect there to be more scores, you know, if this followed a normal curve, we would still expect 26% of the scores to fall out here, or excuse me, 16%, right? So this can't be normal. Among freshmen at a certain university, scores on the math SAT followed a normal curve with an average of 550 and a standard deviation of 100. Fill in the blanks and explain briefly. Okay. This time I'm going to learn from my last opportunity to fill in the blanks and remember to read these very closely. A student who scored 400 on the math SAT was at the blank percentile of the score distribution. Okay, well, we are going to need to do some calculations for this. We know our mean is 550. And our standard deviation is 100. And we want to know the percentile of a score of 400. So we first need to convert 400 to a z-score. Or the raw score minus the mean divided by the standard deviation is going to then be, our formula will be 400 minus 550 over 100. So this will be negative 1.5. And we can look at that. Let's visualize this on our distribution, because to get our percentile, we're going to plot this point. And remember that a percentile is all the scores below that point. I see your question, Candace, about 6, and we'll go back to it in a moment. So we'll go to finish up here. Oops. We'll go to our z table and find 1.5. And then we get our area beyond z is 6.68. And so they were at approximately the 7th percentile. To be at the 75th percentile of the distribution, a student needed a score of about blank points. Okay, now we're just going to find the spot on the distribution that represents the 75th percentile, and then we'll find that z-score and then convert back to a raw score. So our 75th percentile, let's say it's right here, and that's the area where 75% of the distribution is below. So if we know 75% is below, we know this is also the z-score where 25% is above. So we can just find in our table the area beyond z that's equal to 25%, and then that will be our z-score of interest here. Here we have it, 0.67. And now we just need to convert back from our z-score to a raw score. X is equal to the z-score times the standard deviation plus the mean. And that's going to be equal to 617. Does that all make sense? I'm going to guess so. By request, let's look back at 6 for a minute. I realize this is conceptually a little more difficult than some of our other problems, so let's think about it, think through it again. The key thing to remember here about the question is that they're asking, did the SAT scores follow a normal curve? So I found these percentages by assuming a normal curve. I assumed a normal curve, and then I said, does the data fit that expectation or the normal curve assumptions? And I went with, to address this question, I went back to these basic numbers we're supposed to remember about the normal distribution. We know that within one standard deviation from the mean, there's going to be 34% if the distribution is normal. And in this data set, if our highest score is 178, we would expect about 50% of the distribution to fall between these two scores. So this can't be a normal distribution. So does the data fit the normal curve assumption? No. Okay. True or false, and explain briefly. So this gets back to the last topic in your chapter, a change in scale. And we didn't go over this in lecture because it was so brief, and I knew we would do this problem now. So let's think through these answers. If you add 7 to each entry on a list, that adds 7 to the average. This is true. Oh, sorry. So you add, you add 7 to each entry on a list, that adds 7 to the average. Should we illustrate these numbers with some examples? Let's do it with a very small data set. let's say I have some data that are, my data set is 2, 4, and 6, whatever. I'm just picking some numbers so we can look at these. So if you add 7 to each entry on the list, it adds 7 to the average. Well, if we got the average of these numbers, it would be 4. I planned this to make it simple like that. So let's say we added 7 to each of these. And they would be 9, 11, and 13. And the average would be 11. So yes, it adds 7 to the average. If you add 7 to each entry on a list, that adds 7 to the standard deviation. Well, this is going to be false because, as you can see, when we add 7 to each entry on the list, the amount of each deviation stays the same. So you can see that if this is our mean here, and we want to find the standard deviation is dependent on the deviation from the mean, our mean deviation, our deviation from the mean for the scores below is 2, and for the scores above it's 2, and that's true regardless of whether you've added 7 or not. Oh my goodness. If you double each entry on a list, that doubles the average. Well, let's continue our list. So if we double these, I don't know that we need to do the math for this because it's the same thing as if we added 7. If we add the same number to each, or I guess it's not quite the same. Let's just work it out. So if you have, our list is 2, 4, and 6, and we're going to double each, then they become 4, 8, and 12. And our average is 8 instead of 4. So everybody see that? So that doubles the average. That's true. If you double each entry on the list, that doubles the standard deviation. This is going to be true. And let's again look at this, why this is true. So here we've doubled each number on the list already, and we have our deviations. Let's look at the deviations for each set. So here the deviation is 2 and 2. And then if we look down at our doubled data set, now our deviations are 4 and 4. So yes, our standard deviation doubled. If you change the sign of each entry on a list, that changes the sign of the average. Well, let's this is going to be true. And let's look at why. So here's our core data set. Negative, now we changed the sign, so they're -2, -4, -6, and now our average is -4. So that changed the sign of the average. And finally, if you change the sign of each entry on a list, that changes the sign of the standard deviation. This is going to be false. I don't even need to do any math because the standard deviation has to be positive. You cannot have a negative standard deviation. Why is it positive? Well, because when you compute the standard deviation, all the deviations from average have their signs changed when you square the numbers. So let's remember that our formula for the standard deviation is the sum of the deviations squared divided by n, the square root of this whole thing. But remember that when we square these scores, the signs don't matter anyway. So if we went through and computed the standard deviation from these numbers, it'll always be positive. Okay. Now we're almost done. Which of the following are true or false? Explain and give examples. The median and the average of any list are always close together. Well, this is false because, why is that false? Because the median and the average are only the same or very close together when you have a normally distributed variable. If your variable is not normally distributed, for example, if there's positive or negative skew, then the median and the average will not be close together. Half of a list is always below average. Can this possibly be true? What do you think? It's always below average. Somebody out there in the audience. That's right. Half of a list is not always below average. Half of the list could be, it depends again on a normally distributed variable. So if your variable was normally distributed, then half of a list would be below the average, but this is only true for a normally distributed date variable. Next, we have a large representative sample. The histogram is bound to follow the normal curve quite closely. What do we think? Is data always going to follow a normal curve as long as there's a large sample? That's right. This is false. Again, if we had a large representative sample, the histogram is bound to follow, the histogram will follow a normal curve only if the data is normally distributed. For example, if you look at the income data on page 88 of your book, it has a long right-handed tail, and these data are from a large representative sample, but they're not normally distributed. If two lists of numbers have exactly the same average of 50 and the same standard deviation of 10, then the percentage of entries between 40 and 60 must be exactly the same for both lists. Anybody want to guess out there? We've got a trend going, so if you follow the trend, you'll probably be right if you say this one is false. Why is it false? Well, this is only going to be true for normally distributed variables. So, for example, if the histogram for a list follows the normal curve, the percentage of entries within one standard deviation of average will be around 68%. Otherwise, the percentage could be a lot different, and it is possible to have these two variables have the, which they call lists of numbers, two variables could have the same average of 50 and the same standard deviation, but be differently distributed. So you're doing really great, everybody. We're almost done. And we're spending a little more time than normal on this chapter and these problems because it's very important and it's going to be heavily covered on the exam. And with the exam so close, we're considering, this practice as part of preparation. I mean, all practice is part of preparation. So I guess that's always true. For women aged 25 to 34 with full-time jobs, the average income in 2004 was $32,000. The standard deviation was $26,000, and 1/4% had incomes above 150,000. Was the percentage with incomes in the range from 32,000 to 150,000 about 40%, 50%, or 60%? Okay, just a moment. Okay, so we need to, for this one, so if the average income was 32% and the standard deviation is 26, or not, the average income was $32,000 and the standard deviation was $26,000, this variable doesn't seem normally distributed to me. And what I can tell from this information is that, I hate it when it does that. If our average is going to be around here, And how do I know this can't be normally distributed? Well, I'm going back to that idea that 6 standard deviations is going to contain the whole data set, and we would expect then for there to be approximately 3 standard deviations below the mean. And the mean, if the mean is 32,000, that's obviously not possible if the standard deviation is 26,000. So we know we have incomes way out here at 150,000. So this distribution is quite skewed, right? If the mean is way down here, well, the mean will be approximately here. Some other things we know about a skewed distribution are that the median is going to be well below the average. The median is going to be approximately here. And the median is the point where 50% of the scores are below that point. So was the percentage with incomes in the range from 32,000 to 150,000 about 40, 50, or 60%? Well, it's going to have to be 40%, because the 50% has got to be below the median. And since this is a positively skewed distribution, the 50% is below the mean. More than 50% is below the mean. Okay. We're so close. Here we go. 2 more problems. In one term, about 700 statistics 2 students at the University of California, Berkeley were asked how many college mathematics courses had they taken other than statistics 2. The average number of courses was about 1.1. The standard deviation was 1.5. Would the histogram for the data look like 1, 2, or 3? Well, let's think about this. If the average number of courses was 1.1 and the standard deviation is 1.5, this is telling us that, again, we have a positively skewed scenario. So let's look at some of these other options so we can see clearly why this must be positively skewed. So again, if we had given these data, we want to map it onto these distributions and see if it makes sense to decide if this is normally distributed, or to answer this. So if the average number of courses is 1.1, the standard deviation is about 1.5. Well, there's no space for even one standard deviation here, so it can't be 2. If we look at 3, because one standard deviation we would have, even at a score of 1 standard deviation, we'd have negative 0.4 courses. That's not possible. Now, if we go over to our histogram on the far right and we, we know our mean here would be about right here. And the scenario is even worse here. So there's clearly not space in this tail for an appropriate number of standard deviations. Hi, it's okay. So here with this distribution, we know our mean is going to be approximately in this location. The skew always pulls the mean in the direction of the skew. Excuse me, kitty. Sorry. Hold on just a minute. And so we have, if we have a standard deviation of about 1.5, we know that some students took a lot more courses than 1.1, because with a big standard deviation like this, we know that there must be more, there's some students with a much higher number of courses, like maybe 4, for example. So we've, you can only have a large standard deviation like that if you've got a big spread in the data. A normally distributed distribution doesn't have enough room for that spread. This one doesn't have the spread going in the right direction. Only number 1 can be correct. Does that make sense before we move on? More or less. Oh, super. One final problem. In 2005, the average score on the math SAT was about 520. However, among students who took a subject matter test, the average score on the math SAT was about 624. What accounts for the difference? Well, this is a thought problem. What might be different among students who just took a standard SAT versus those who took a subject matter test? Well, we can assume that students who take the subject matter tests are applying to better schools or more competitive programs. So they're probably students who are already more likely to score higher on the SAT. Does that make sense? Okay, excellent. Okay. This concludes our coverage of the review exercises for Chapter 5. If you have any questions about how we found these answers or how to do these problems, I encourage you to make sure that you watch part 1 of this lecture and make sure you feel comfortable with this material for our exam. Remember, for the most efficient way, do some stats every day.